So hi and hello there. Welcome to the new video of the course, and in this particular video we are going to see a very first gate, that is NOT gate. Okay, so without wasting any further time, we'll straight away jump to this particular concept of NOT gate. So first we'll try to understand what is the function of NOT gate. Okay, so I'll write over here very shortly. NOT gate performs inversion operation. NOT gate performs performs inversion operation. Inversion inversion operation. What does that means? See, remember one thing, whenever you will listen to this particular word, that is inversion. So meaning of inversion is opposite. opposite opposite. So basically those students who had learned the concept of BJT from me, right? So during the amplifier section, when we were dealing with this particular uh, concept of BJT, right? So what we used to do, we used to give we used to provide this input signal to the BJT, right? And at the output side we were getting the amplified signal, but it was inverted, something like this. So as you can see, it was 180 degree out of phase. This particular signal, it is 180 degree out of phase with respect to the input signal. So this particular signal is known as what? Inverted. So remember one thing, whenever you will listen to this particular term in electronics, so inversion means what? Opposite. To get the opposite kind of signal, right? Okay, and this is the symbol of the NOT gate, as you can see over here. So this is the symbol of NOT gate. Okay, a triangular like shape, and at the end of it a circular like shape is present. So this represents that a negation would be there. So we'll see what exactly this negation is. Okay, so for that what I will do, as I told you over here, NOT gate performs inversion. Okay, so uh, what I will do, just a second, I will take one input. Let's suppose this input is A. Okay, let's suppose this input is A. Just a second, let me take certain different color. This will do. So let's suppose this is input A. Okay, let's suppose the value of this particular input is 1. That means what? I am providing logic 1 to the input of this particular NOT gate. Okay, and as I told to you over here, NOT gate performs inversion operation. That means what? It will provide opposite signal. So obviously at the output side you will get the values. Let's suppose your Y, I will consider this particular output as Y, which is 0. Okay, that is logic 0. That means what? Long story short, if I want to show you with the help of this analog kind of, analog electronics, so what I'm doing over here, just a second, yeah, I'm providing plus 5 volts, that is logic 1. I'm providing plus 5 volts to the input side of this of the NOT gate. So this is the input side and this is the output side of the NOT gate. Okay, and to the output side I am getting the output as minus 5 volts. Okay, so long story short, what exactly we are going to get, and if at the input side, if I'm providing what, if I'm providing logic 1 or plus 5 volts for example, so at the output side I'll get logic 0 or minus 5 volts. Okay, I hope you understood this particular point. So let me erase it and let me just a second, let me just right let me just fill this particular table. Okay, but before coming to that particular part, just a second, yeah, I'll take blue one. Yeah, so as you can see over here, this is your A. If I'm providing logic 1, right, this is logic 1 is your A, and over here Y is 0, right, because it is performing inversion operation. So this particular thing, it is also known as, this particular value Y is equals to 0, it can also be written as A bar or A negation. So this particular thing, it is known as what? Negation. Okay, negation. So henceforth in digital electronics, whenever you will see such kind of symbol, okay, that means this one, this circular kind of symbol, okay, in front of some gate, so that is more, that means what? That means negation. That means inversion operation is going to take place. That means what? That means inversion operation is going to take place. Remember this particular point very, very clearly. Okay, so this is your A bar. So Y is equivalent to A bar. Just a second, yeah, Y is equivalent to A bar. Alright, so now I'll write over here. So this is your A, right, that is your input A, and Y, which is nothing but, that would be inverted form, right? Y is equivalent to A bar. This is what we had seen over here. So what I'm doing over here at the input side, if I'm at the input side, if I'm providing logic 1, right, at the output side I'm getting logic 0. Okay, on the similar note, if I'm providing, just a second, if I'm providing uh, a is equals to 0 at the input side, so obviously at the output side, that is why I would be getting logic 1, which is nothing but a bar, right? So remember one thing, I had seen generally most of the students, they get confused whenever they see this particular term a bar, or maybe any other variable, maybe a bar, b bar, they inherently assume that this a bar is 0. No, it solely depends on a. So if your a is 1, so your a bar would be 0. On contrary, if your a is 0, your a bar would be 1. Okay, depends on a, what exactly the value of a is, and depending on that, the value of a bar changes. Okay, so let me erase this particular thing, and now we'll fill this particular table. So this is 0, right? So if I'm giving 0 to the input of the NOT gate, I would get 1 at the output side of the NOT gate. Okay, now we'll see the designing of the NOT gate with the help of a transistor, that is bipolar junction transistor. Alright, so for that, what I had done over here, just a second, so for that, what I had done over here is I had taken this particular BJT transistor, as you can see, and as of now, we are not at all interested in the values of resistor, because that's the part of analog electronics. And I had, like in my previous course, I had told you how to find these particular values and all. So here we are not at all interested in this particular part. Here we are just interested in the working of BJT, especially in the cutoff and saturation mode, and then we'll see what exactly we are getting at the output, right? So what I am doing over here, so over here I am providing input voltage. I'm providing input as square wave, that means this plus minus 5 volts. So this is plus 5 volts, this is minus 5 volts, this is plus 5 volts, this is minus 5 volts, or else what I would call over here, this is logic 1 and this is logic 0. Okay, since we are dealing with digital electronics, so we call the upper half, that is the positive value, or the higher value, as 1 and lower value as 0. Okay, this we had seen in the previous session, so I hope you are familiar with it. Okay, and based on the input we are governing the output, right? So first of all, what we'll see, first we'll deal with logic 0. Okay, so when my input is 0, I'll write over here, when my V in or input is logic 0, then we'll try to analyze the analyze this particular transistor circuit. Okay, so see, when my input is 0, I had already told you, when the input for the BJT transistor, it is 0, right? So what is going to happen, my transistor is going to be in the off condition, or it would be in the cutoff region, right? It would be in the cutoff region, or it will behave as an open switch. Okay, so over here, this particular transistor, it will behave as an open switch. But when my input is logic 0, remember to this particular point very, very clearly. Okay, remember this particular point very, very properly. Just a second, I just forgot to write this RC over here. So this is your RC, I'll write over here, this is my RC, and this is over here, this is my RC. Okay, all right. So basically now since my input is 0, right, my input is logic 0, or I'm giving minus 5 volts to the input side. Okay, so that's why my BJT or my transistor would be in the cutoff region, or it would behave as an open switch. So as you can see, it is behaving as an open switch, and we had already seen that in an open switch condition, my output current or IC would be 0, right? Okay, it would not flow in this particular branch. Okay, this is what we had seen in the previous session as well. So now how the IC will flow, so over here my IC will flow in this particular direction. That means what, my V out would be logic 1. Now I know, I had seen most of the students getting confused over here. They will ask me, sir, over here as well, see over here, this particular terminal, it is open circuited. No, it is not at all open circuited. Over here what we are doing, we would connect load resistor RL. Okay, but during representation we show this particular thing in this manner, V out. Okay, in actual scenario or in actual circuitry, we would connect one load resistor. Okay, this can be anything, maybe a fan, maybe a LED, maybe a resistor, it can be anything, but during representation we show it in this way. Okay, but inherently you have to assume that there is one load resistor. Okay, I hope you understood this particular point. So now what is going to happen, this current will go over here and then it will see that over here the circuit is open, right? It will act as an open switch, so it will not go or it will not pass through this particular branch. Why? Because current always flows from that direction where the resistance is minimum, and it will see that here the resistance would be less as compared to this branch, and therefore the current IC will flow over here. That means what, my V out would be logic 1. Let me write over here, my V out would be over here, my V out would be logic 1, V out would be logic 1 or high, I would say. Okay, now we will move to the next condition, where what I am doing, I am keeping my V in as logic 0. So I am keeping my V in, just a second, I am keeping my V in as logic 1. I will keep my V in as logic 1. Okay, that means what, I am providing higher voltage to the input side. Let's say it is plus 5 volts for our understanding purpose. So what is going to happen, as soon as I am going to provide higher voltage to the input side, so obviously this particular transistor would be in the saturation region. That means what, it will act as a closed switch. Just a second, I will write over here, it will act as a closed switch. So that means what, this particular terminal which was open over here, this would get short circuited, something like this. And now what is going to happen, since it is getting short circuited, so my current IC, see in the earlier case it was flowing in this particular direction, okay, IC, but now over here it will see that over here, let's suppose there is some load resistance RL over here, RL, you can take anything. Okay, the current I, it will flow up till here, maybe up till this particular point, and then it will see that over here it would get maximum resistance and over here it would get negligible resistance. So therefore the current I will flow in this particular direction, or IC over here, the current IC will flow in this particular direction. I hope you understood this particular point. Just a second, let me erase this particular thing. Just a second, yeah. So over here the current IC, I'll write over here in this way, yeah, the current IC, it will flow in this particular direction. And since over here at the input side there isn't any current, right? So we all know what V is equivalent to I into R, right? Over here we are dealing with output voltage, so here it would be V out. As you can see over here it is V out, and over here the current is 0, and if the current is 0, that means over here it was IC, right? IC was flowing in this particular terminal, it was not at all going to this particular branch, right? So what is going to happen, therefore my V out would be 0. So over here what we would be getting is, let me erase this particular thing, okay, and let me write over here. So my V out over here in this particular scenario, V out would be logic 0. V out would be logic 0. Okay, that means what, see over here, as I told to you, in the case of NOT gate, like when we started the NOT gate, so when we were giving minus 5 volts or logic 0, over here as well I had written over here, when we are providing minus 5 volts or logic 0 over here, we were getting logic 1, okay, that is A bar. So let me write over here, okay, just a second, let me write that particular thing over here, so that whenever you will refer my PDF you should not get confused that what is logic 1 and logic 0 and all. Okay, maybe let me select some vibrant color, maybe this one, yeah. So yeah, this logic 1 indicates that I'm giving, just a second, let me move somewhere over here, okay, and this particular thing I will move somewhere over here, okay, all right. So this logic 1 indicates that I'm providing plus 5 volts, okay, you can take any amount of volts, maybe 1 volt, 2 volt, but generally we prefer 5 volts, okay. If I'm providing plus 5 volts to the input side, I would be getting minus 5 volts to the output side. On the similar note, if I'm providing minus 5 volts to the input side, that is logic 0, I would be getting plus 5 volts to the output side, right? So same goes over here. As you can see over here, this logic 0 indicates that if I'm providing minus 5 volts, okay, for your convenience I'm writing minus 5 volts. If my V in is minus 5 volts, so my V out would be plus 5 volts. Okay, this is my V out. Okay. On the similar note, if I'm providing logic 1, that is if I'm providing my V in as plus 5 volts, okay, I'm getting V out as logic 0, or I can also write it as V out would be minus 5 volts. Okay, I hope you are understanding this particular point. Okay, so basically now with this particular transistor, what we can say that we had designed a NOT gate. Okay, I hope you are getting this particular point. With this particular transistor, we are able to design what? We are able to design a NOT gate. So now what we'll do, let me take this white color over here and let me write certain things. So this is my V in, or the input voltage. Then there is my transistor, right? When I'm fetching, where I'm fetching this particular input voltage, I'm fetching this particular input voltage to the transistor, that is BJT transistor, which is T1, right? How exactly it is behaving, that is what we are going to analyze over here. And then I'm taking out my output voltage or V out, right? So now see over here, when I'm providing, or basically when I'm giving minus 5 volts or logic 0 to the input voltage, sorry, to the input side of the BJT, right? So if I'm giving logic 0 to the input side, what is going to happen? This T1 would be acting in the cutoff region, okay, or it will act as a closed switch. So basically my transistor will operate in the cutoff region. Cutoff region, write it in short form, this is cutoff region, or basically it will act as an open switch. Okay, and this V out at the output terminal will get the value as logic 1. Okay, we'll get the value as logic 1. Okay, on contrary, if I'm giving my input if I'm providing the input voltage as plus 5 volts or logic 1 in short, right? Since we are dealing with digital electronics, so henceforth I would be only using logic 1, since this is the very first gate that we are dealing with. So that's why I had used I'm using logic 1 and plus 5 volts, so that you should not get confused. Okay, and when I'm providing higher voltage to the input side of my BJT transistor or bipolar junction transistor, so what is going to happen? My T1 of the transistor is operating in the saturation region. Saturation region. Okay, again I'm writing it in the shorter form. And in this particular scenario, this T1 or my BJT transistor, sorry, bipolar junction transistor, it will operate as a closed switch. Great. And then at the output side, since it is acting as a closed switch, I will get logic 0 or minus 5 volts. Okay, so now I hope that you understood the concept of NOT gate. Okay, but in reality, if you could see over here, now you will ask me, see, this is just a symbol. In reality, if you could see over here, just a second, let me change the pen. Yeah, over here we have plus VCC, okay, and one ground. But over here, when we are dealing with NOT gate, now you will say me that, sir, over here the VCC is absent and even the NOT gate is absent. Yeah, that's also, sorry, ground is absent. So that is true, but this is just a symbol. Okay, so most of the times I had seen the students, they don't see this particular small detailing part. Okay, and this is where they fail. But since you are learning from me, you expect to understand that what exactly it is. Okay, so over here this is just a symbol, okay, or you can consider it as an ideal case, but in reality NOT gate has VCC and ground. So basically this is how NOT gate looks. So as you can see over here, this is the chip or the IC for the NOT gate. This is chip or the IC for the NOT gate, and the number for this IC is 7404. This we will see again in the next session as well, but just to explain this particular thing over here, what you can see, there are 1 2 3 4 5 and 6. So there are 6 NOT gates or 6 inverting gate. Okay, so the first pin over here, you are taking input from the first pin and you are getting output from the second pin. This goes on, okay, up till 6 pin, and the 7th pin is reserved for ground. So that means what? for all these NOT gates. So basically all these NOT gates contain one BJT transistor. So just a second, I'll just show you this particular thing so that you should not get confused that how exactly these things are happening. Okay, so just now don't consider it as a NOT gate. Now think it as a BJT transistor. So this is your BJT transistor, right? And this is grounded, and over here you are taking input. Okay, over here you are taking input. Similarly over here there is one BJT transistor. Okay, this is emitter, this is collector of the transistor, right? And over here same goes with this particular transistor as well. I'll just show you with the help of this three transistor. This is emitter, this is collector, right? Okay, and over here see this collector side, obviously there would be some resistor over here. It would be connected to all of this particular collector. Okay, and this would be connected to the collector. Okay, this VCC would be connected to the collector, and this emitter would be shorted in this way. Internally it is all happening internally, and then it is grounded, so basically over here you are getting common ground and a common VCC. Okay, and over here basically you are taking the input. Over here you are getting the input, right? You are getting the input. I hope you are able to understand this particular diagram. Okay, I had not drawn it properly, but just with the help of this particular thing you are able to understand. This is the common RC. Okay, so remember one thing, whenever you are dealing with chips or ICs, right? So in ICs you would get a hefty amount of gates. Okay, so for that gates there would be common VCC, as you can see over here. See over here we were providing only one VCC for the single transistor, but now over here the case is different, since there are 6 different what I can say transistors. Okay, or 6 different NOT gates, and we all know that each NOT gate contains one BJT. Okay, so it is not at all possible to make a separate VCC and ground for a NOT gate. Okay, because it will for single NOT gate. Okay, and over here there are 6 NOT gates, so for 6 NOT gate you would be requiring 6 VCC. Okay, and 6 ground, so it will take a hefty amount of space. So what researchers did, or those who fabricated these particular chips, what they did, they make a single VCC, okay, and a single ground, and a single ground. Okay, and then what they did, they connected it to the NOT gate. Internally, as you can see, the transistor, the collector side of the transistor, they are short circuited, and the emitter side they are short circuited, and the collector side is connected to the VCC, and the emitter side it is connected to the ground. Okay, and over here, depending upon your project and all, you may use any of this particular NOT gate. If I want to use only this one, that means the first one, I may use this one. If I want to use all 6, it's up to me, I can use all the 6. Okay, now most of you guys will ask me, sir, why there are only 6 NOT gates, why there aren't 8, or there aren't any less than 6? So my dear student, as you can see, according to the symmetry of this particular IC or this particular chip, that is 7404, so over here 2 pins are reserved for VCC and ground, okay, respectively. That means one pin is reserved for VCC and another is reserved for ground. Okay, so basically there are 14 such pins, right? And we deduct 2 from it, so we are left with 12, right? So there are 14 pins. Okay, 2 are reserved for VCC and ground, so now we are left with only 12. And you have to see over here, for one NOT gate, for one NOT gate, we have two pins. Why 2 pins? One for input and one other for output. Okay, so basically we have, so what you can do, since this is 12, so you have to divide by 2, so these are 6. So that means what, there are 6 such inverting amplifiers, not amplifier, extremely sorry, there are 6 such inverter, or there are 6 such NOT gates present in this particular IC 7404. Okay, so I hope you understood this particular concept. And now what we'll do, now since we had dealt with the designing part of this particular NOT gate, so what we'll do, we'll we'll simulate this particular circuit which we had deal. We'll simulate this particular circuit on the Proteus software. And so I had designed this particular circuit over here. Let me just zoom it out. Sorry. Let me relocate it properly. Alright. So what I'm doing over here, I'm feeding the square wave to the input side of the BJT, and as I told to you, over here at the output side, just a second. So this is my output Vout. This is my Vout, and as you can see over here, this is my load resistor RL. And during the explanation, I told you that this RL can be anything. Over here, it is LED. Okay. So this is my input. So this is my plus minus input, right? And to the input side, what we are giving, to the input side we are giving, or we are fetching a square wave. That means what? I'm providing this kind of signal to the input side of the BJT over here, and this we are observing with the help of oscilloscope. So this is my oscilloscope. Okay, I hope you know how to use this particular thing because we had seen in the previous course. Okay, this is my resistor RC, this is my resistor RB. Okay, just now we had seen this. Okay, and this is plus VCC that I told you, which I had kept it as 3.33. okay, let me erase all of these things which I had written over here. Great. Now what we'll do, we will run this particular simulation, and then we'll try to analyze this particular thing. Okay, so let me run this particular simulation. Alright, so let me just bring it over here. This is my VCC. I hope you are able to see it. Okay, so now we'll see how exactly the things are going. We'll bring it over here. See, just a second. Yeah, I think now it is fine. So as you can see over here, whenever the waveform it is moving in this particular direction, that means what? If I'm providing logic high, okay, this is what? This is your logic 1. Okay, logic 1, and as you can see over here, the amplitude is plus 5 volts. That means what? Your waveform is moving in this way, plus 5, minus 5, plus 5, minus 5. So this is your plus 5, this is your minus 5 volts. Okay, so during plus 5 volts, as you can see over here, yeah, as you can see, the LED is in the off condition. See, once again, when this particular waveform it is operating in this way, I'll just erase this particular thing so that you would see this particular concept clearly. Alright, so as you can see, as you can see over here, during this half, or during the logic 1, okay, during logic 1 the diode is in the off condition. Again, if you are able to see, so that's why I had slow down this particular process. That's the different scenario, that we are not exactly getting the square wave. There is some reason for it. Okay, the reason we will see in the analog electronics, so you need not to worry about that. I am not at all interested in that part as of now, since we are dealing with digital electronics. So as you can see, during logic 1 you are getting you are seeing that the diode is in the off condition, and during this particular scenario, that is logic 0, the diode is in the on condition. I hope you are able to see that. Okay, sorry, yeah, again I'd slow down this particular process. Let's see if you're, yeah, just a second. I know this particular waveform is a square wave, but now it is taking some different shape. That's the like, there is some reason for it that we'll see in the analog electronics. You need not to worry about that. Okay, what I want to show you is this. Since we are dealing with digital, so as you can see, during logic 1 the diode is in the off condition, and during logic 0 the diode is in the off condition. That I will increase the frequency. Yeah, as you can see, Now I think it is crystal clear to you all guys. During logic 1, during logic 1, the diode is in the off condition, and logic 0 it is in on condition. Oh, see over here once again, off, on, off, on, off, on, off, on, off, something like this, right? So whenever the input voltage is in the positive half cycle, so your diode would be in the off, and whenever the input is in the negative half cycle, the diode would be in the off, on condition. Okay. So now that you had understood this particular concept, I hope you enjoyed this particular session. So if you have any doubts, feel free to ask me at any time. I'll surely help you. Okay. So thank you for listening patiently. I'm ending this video over here. Thank you.